Well, hello ladies and gentlemen, and welcome to the next step in our computer build. Now, in the last video I promised you that we would have some form of outputting some data from our computer, not via, a more impressive computer, which is the Arduino Mega, into a much more impressive computer, which is my laptop. So we're going to do it with this chip here, and this chip is a W65C22. Now, given that our processor is a W65C02, you can tell that this chip is designed to work with our processor, so it should be fine. And as with all things, we're going to start by going and having a look at the data sheet. So let's have a look. Well, straight away we can see that we've got our 8 data pins coming from and to the processor. And if you have a look on this side, we've got 8 port pins here for port A and another 8 port pins here for port B. So this chip has got a lot of tricks up its sleeve, and it can do a whole bunch of different things with the data, either throwing it out to one of 2 different places or receiving it from one of 2 different places and doing something to it and throwing it back at the processor. And actually we're not even going to come close to looking at all of the functionality of this chip, at least not in the next couple of videos. We're going to have a look at how it does one thing, but the point is, if it does loads and loads of different things, then there also needs to be a way of telling it what thing you want it to do. So let's have a look at some of the other pins before we do anything. Look, we've got VSS and VDD, so that is the power supply. We've got a reset, just like the processor has. We've got a Phi2, which is the clock. We've got a read-write pin, that can go to the read-write pin of the processor. This all helps it to do what it can do. But most important, we've got these, RS0 through RS3. And RS stands for Register Select. So in other words, there are 4 pins that control 16 registers. Don't forget that 4 binary bits can produce 16 different numbers. So let's just remind ourselves of what a register is. So a register is an 8-bit, in this case, number, which can tell us information, it can store a number, and it can tell the processor to do things. So, each of these registers, and here they all are, register 0 through register F, which is all of these pins here from 0000 all the way through to 1111. Okay, each of these registers either accepts some data and tells the chip to do a thing, or the chip does a thing and sets some of the digits on these registers that we can read and tell us what it's just done. I'm not going to go through all of these. There's loads of cool stuff to do with timers and to do with interrupts, which is when you interrupt a program because someone's pressed a button, or all sorts of interesting things. But we're just going to have a look at these first 4. So, the first, in fact, we're looking to look at register number 2 and register number 3 first. And these are just data direction registers for B and A. If we go back here, we can see we've got port A and port B. And all these are going to do is tell us whether port A and port B are inputs or outputs. So let's go and have a look at registers number 2 and 3. So here we are at the table which tells us what registers 2 and 3 do. And this is the data direction register. So, what you do is you send an address 2 to the chip, and if it is 2, then that is for data direction register B, and if it's 3, then it's for data direction register A. And for each, you send an 8-bit number, and for each of these things, if it is a 0, then that pin is an input, and if it is a 1, then it is an output. So, for example, if I sent the address 3 and the number 00000000, then it would set all of port A to be an input. And if I sent to address 2 and sent 11111111, then it would set all of port B to be an output. So there's 2 of the registers, and then the other 2 we want to have a look at is register number 0 and register number 1, and it depends on whether they are an input or an output, but if they're an output, then whatever I write to register number 0 will be outputted on port B. If I write to 0001, then whatever number I write to 0001 will be outputted on register A. And if they're inputs, then when I read from these, the number will be read in on the data pins. If I read from this one, this number will be read in on the data pins. So what these are effectively is latches, right? I can write just momentarily in one clock cycle a piece of data to port B, and it will stay there until I write another piece of data to it. And I could also write a piece of data to port A, and it will stay there until I write another piece of data to it. The best way to look at this is going to be via an example. But for the moment, let's concentrate on wiring it up. Okay, when we're wiring it up, there's plenty of pins that are pretty obvious where they're going to go. The data pins are going to go to the data pins, to the data bus. VSS and VDD are going to go to the power supply. Read-write is going to go to the read-write bus. Clock is going to go to the clock bus. We've got two chip select pins, which I'll talk about later. One of them, the chip will only work if it's high, and the other one, the chip will only work if it's low, and they both have to be respectively high and low for it to work. We've got a reset, which needs to go to the reset button for the whole computer. And then we've got various pins that we don't care about just for the moment. However, we do have ourselves a slight problem, which is that we want to write to address 0, 1, 2, 3, 4, 5 all the way through to F. But that's not how our data bus works. Our data bus is a 16-bit data bus. So we've got to somehow find a sensible set of addresses to write to. So let's go across to the pad and have a look. Okay, so we want to write through to 0 through F, which is going to be 0000 through 1111. But we've got to have a whole bunch of other addresses to write to. Now, on our particular computer, if you remember, the addresses 8000 through FFFF are already taken up by the ROM, so we can't use those. So for the sake of simplicity, I'm going to use the address 600 and then 0 through F. So in other words, we're going for all our different functions. We're going to write to address 6000, 6001, 6002, and so on, all the way through to 600F. Now, if we have a look at what the binary of that is, 6 is 0110, 0 is, of course, 0000, 0 is 0000, and then our final one is going to be 0000 through 1111. So what we need to do is we need to find a way to allow the computer to write to this, some sort of address logic that's going to only allow the chip to work under those circumstances. And we can do that. So to help us do that, we're going to bring in this chip here. Now let's go back to our computer and we're going to have a look at the data sheet for this chip. This is called a 74HC688. And what it does, it's a comparator. So we've got 8 lines here. So let's say this could be the first 8 lines of our address. And we can tie Q0, Q1, Q2, Q3, Q4, whatever, high or low with the resistor. So let's say we tied Q0, Q1, Q2 and Q3. We tied them to be low, high, high, low, for the sake of argument. What this chip does is it looks at P0, 1, 2 and 3 and it says, are they the same as Q? Are they low, high, high, low? If they are not, if anything is not the same, it outputs a high. But if they all absolutely line up perfectly, it outputs a low. So in that way, we can use resistors to set a really specific address that we want. And if the computer writes to any other address than the ones that we want, it won't get through. And that's pretty much exactly what we need. Okay, that is pretty much precisely the purpose of our address logic. So let's go back to the piece of paper and we'll see how it might work. So we've got our W65C22 chip, and it's got register select 3, 2, 1 and 0, and they can go directly to address lines 3, 2, 1 and 0. No worries. Unfortunately, we've also got all these address lines, that we have to deal with. And what we're going to do is we're going to plug all of them into two comparators. These comparators are our 75HC688, and we're going to check to make sure that these address lines are exactly as we want them. We want them to be 0, 1, 1, 0, 0, 0, 0, 0. For these first 8. And if they are all perfect, then it will output a 0, which we can feed into this chip that will make it work. And so if these are all perfect, this one's going to check for 0, 0, 0, 0. And by the way, the other 4 inputs on this comparator we're just going to set to be the same. We're going to manually tie them to be the same as their comparators, so they won't matter. And so if all of this address is perfect, if it is all 0, 1, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, then this will output a 0. Otherwise, it'll output a 1. And if we plug this into chip enable bar, then when it is 0, this chip will work. And when it is 1, this chip will not work. So we can use two of these little ICs to tie them together to make sure that only the address 600 will get through to this chip at all, and then 1 or 0, 1, 2, 3, 4 and so on, all the way through to F, will do all of the 16 various different things this chip can do. So what I think I'll do is I'll wire it up in stages and show you exactly what I'm doing as I go. So let's do that. All right then, so here we are with the chips laid out on the board. Now, our first job is to connect power and ground cables. Now, I don't intend to continually refer back to the data sheets for that. I think you can probably take my word for where they need to go. So I'll get on with that, and then I will get back to you. Right, that's the power cables connected, both the chip, positive and negative, and also for the address logic. Now, we're going to start with this address logic chip at this end, and we're going to work our way from left to right. So the first thing I need to do is I need to tie the output enable low. That is a low signal, so that means that the output is always enabled on this chip. Okay, now the next thing I need to do is program the first 4 bytes of my address. So if you remember, we want to write to address 6000 through 6000F. So the first 4 bytes of that would be 0110, which would be a 6 byte, and that's what I want it to be. And then the pins in between are what's going to come from the address bar and address bus, and that's what it's going to compare it to. So I'm just going to pause it, and I'm going to put in those 4 address wires. And there we are. The first 4 address lines are connected up. So the first number of our address, if it is 6, it will go to this chip and it will manage to get out and into the next chip. So the next thing I need to do is the next 8 bits, which are all zeros. So I can connect now. I don't actually need resistors if I connect them to 0 volts. But I'm putting in resistors 1 because it looks nice, 2 because they're cheap, and 3 because it gives me the flexibility to put in a different address in the future if I wish to. So another 8 resistors all going to 0, so let's do that. And there we are. We have got the next 8 comparator all set to 0. Just before I put in the data lines, however, I'm going to need to connect the output of the first chip to the output enable of the second chip. And what that will do is, if the first chip meets the criteria, it will then enable the second chip, and then we can check if the second chip meets the criteria, and then the output of the second chip will go onto our 65C22 versatile interface adapter, and then that will work. So I will get the address lines installed, and then we will look at the next section. And there we are. We have got the next 8 address lines tied into the correct places. Now, there's a couple more things to do before I can then move on to the interface adapter chip itself. The first thing is that we need the output from this chip to go into this chip. That's one thing. And then the second thing we will need to do is there are still 4 more comparators here that we're not using. So we have to tie all 4 of those to the same voltage, both the inputs to each other and to the same voltage. Otherwise, we won't get a proper output from the second chip. So I'll just do that now. And here we are. So I've got these final 4 comparators connected to ground as it happens, and I've just connected them across so that they will always read the same thing. And then the last thing I've got to do is to connect the one wire which, with the correct address, will make this chip light up. So that is the output from this, which I will connect here, and it goes into the chip select bar. So this chip has got 2 chip select pins. One is active low, which is the one we want, and one is active high. The one which is active high, in a minute I will just tie high. Okay, so that is that section. The next bit I need to do is to wire up the actual interface chip itself. So let's do that. Okay, we are making progress. So now we need to start thinking about connecting this up. And there are some pins that we want to connect up for future use, and some pins that we want to connect up because we want to use them now. So over at this end, the first pin over here is an interrupt request pin. We're not bothered about that, so we don't need to do anything with it. The second pin in is a read-write pin, and that needs to be connected across to the read-write pin from the processor, so that the processor knows whether it's reading or writing to the outputs or inputs. And then also over here there's a clock pin, which we're not using at the moment, but it's useful to connect it up, so we'll connect it up to the clock of the processor as well. So let's get those done. Oh, and just one more, there is a chip select pin as well. So we've got one chip select pin here coming from the address logic. There's another one which has to be high in order for the chip to work, so we need to tie that high. So let's get those all put in. Okay, here we are. We've got the read-write pin connected. We've got the other chip select tied high. We've got the clock selected, clock connected, sorry. And then these next pins, the next 8 pins, are all data pins. So they need to go across to here. And just like on the 6502, the most significant bit, which is pin D7, needs to go the shortest distance, and then needs to go further and further and further across to the least significant bit, which is the furthest away across to there. So I'll get those 8 data lines connected up. That's our next job. Right, there are all 8 data lines connected up. The next pin we get to is a reset pin. Now, rather than having 2 reset buttons, it's actually easier just to connect both of them to the same button. So that wire runs around like this to the reset button for the main processor, and that's that done. And we're actually very nearly done. The one thing we do have to do is, if you remember, we set up all this address logic here to make sure that only addresses starting with 600 get through. But the last byte of the address, 1 through F, or 0 through F, is going to tell us what what instruction we want this thing to actually do. Okay, and to that end, we are going to have to connect the last 4 of these address lines to the next 4 pins. It is just worth saying that the pins run, instead of running, again, they run backwards basically, so the shortest pin has to go to the first one, and then the longest wire goes from furthest left to furthest right. So I'll get all those connected up, and then I'll come back to you. And there we are done. One chip fully wired up. We have now got ourselves an output. Now, you might be forgiven for saying, okay, but what is the output? And that's not totally unfair, because there's not actually anything for it to output to. But that's not a problem, because don't forget we've got port A and port B there. So what I can do is I can get some LEDs and some current limiting resistors like we did in earlier episodes, like this, and we connect it to one of the ports, for the sake of argument, port B, like this. Then what we have got is a device capable of outputting to these 8 LEDs. Now, okay, I grant you that 8 LEDs, if you're used to, a screen with 12 million pixels, is maybe a little bit on the low side, but it is a start. Also, by the way, there is no significance to the yellow and green LEDs, it's just what I happen to have. So in the next episode, what we're going to do is we're going to try and write a program that will light up those LEDs and make it the biggest, most complicated and most expensive flashing LED. I'll see you next time. Goodbye.